Hello everyone and welcome back to this next lecture in the machines video series, and this is where we had left off in the previous lecture where we had simplified the rotor equivalent circuit. So a little brief recap that we had drawn the equivalent circuit for a single phase induction motor, and we had seen that the stator equivalent circuit, which is the one on the left, is fairly simple, and it is a 50 Hz circuit. On the other hand, the rotor equivalent circuit has a frequency dependent term. Now this frequency dependent term appears because the induction motor is a rotating machine. The rotor is rotating at a speed equal to nr, right? So this nr is the rotating speed of the, or rather is the speed of rotation of the rotor, usually in revolutions per minute. Because of this speed of rotation, the frequency of the rotor is no longer at 50 Hz. The frequency of the rotor is now 50 Hz multiplied by slip. And this slip is defined as the difference between the synchronous speed and the rotor speed divided by the synchronous speed. So it's a kind of a percentage difference in the rotor speed with respect to the synchronous speed. So because of this frequency dependent term, the induced EMF will not be at 50 Hz. It will be much lesser than 50 Hz when the rotor is rotating close to its full speed, or rather either full load speed or no load speed, whichever. So the currents will also be of a different frequency than 50 Hz. Now when the frequencies are different, we found that this slip term appears in the induced EMF as well as the inductance, because when the frequency is different, the inductance also is different because the reactance changes. The problem with this circuit is that from an analytical perspective it was a little inconvenient. The reason, the stator is at a fixed 50 Hz frequency, but the rotor is at a different frequency. So we have these two circuits which are at very different frequencies, which is a little inconvenient to analyze. But we found that with this little bit of a computation, that is all we had to do is calculate the rotor current, found out that this rotor current is the induced EMF divided by the reactance and the rotor resistance. So the rotor resistance initially was independent of slip speed. But if we divide the numerator and the denominator by slip, we find that the induced EMF and the inductance are now free of slip. But the rotor now gets the slip term. The impact of this is now we have the rotor circuit devoid of the slip term. That means we now have the rotor circuit at 50 Hz. And the slip now appears as the rotor. In the rotor, which means that as the rotor begins to rotate, it appears from the equivalent circuit that this equivalent circuit is still at 50 Hz with an induced EMF and an inductance, but the rotor resistance is now much larger due to the slip. Therefore, the currents will be lower. Alright, again, this is only analytically. Physically, the frequencies will change. But we need to analyze the circuit and we need to build a simulation model. That's why we are coming to this. So with this recap, I will now continue the lecture. As always, before I start the lecture, a little bit of brief background that if you're interested in these kind of video lecture series, but you would like something a little more comprehensive, I do have full-length online courses which you can access on my website, which is pythonpowerelectronics.com. So this is the home page. You just have to click on the Learn button, and this will take you to the list of courses. So these are my 5 courses which I have currently, and I'll just go through each of them. The very first one I have is simulating power electronic circuits using Python, and in this I talk about the basics of how you can simulate circuits with Python, and I will introduce the free and open source circuit simulator Python Power Electronics. The next course I have is basics of digital signal processing for power engineers, and in this I talk about how you can use Python and specifically the signal package within SciPy to analyze and design filters for power electronic applications. The next course I have is simulation of magnetics for power electronics using Python, and in this I talk about how you can simulate magnetic components such as inductors, coupled inductors and transformers using Python and Python Power Electronics. The fourth course I have is called Control Analysis with Python for Grid Connected Converters. And in this I talk about how you can use the Python control package along with NumPy and SciPy to analyze and design controllers for power electronic applications. And I have chosen a single phase grid connected converter as an example for all the control cases which I'll be considering. The very last course I have, or the latest course, is a free course called Why Specialize in Power Electronics. And this course is more of a motivational course. It talks about the opportunities and advantages of being a power electronics engineer, and also several of the skills that can be acquired and the job opportunities that are available for a power electronics graduate. So all these courses are available on two platforms. The first is Decibel Labs and the second is Udemy. So you can check it out from whichever of these two sites. The link for this page is provided in the description for this course, or rather the description of this video. So if you're interested, do check out the description of this video. So with this, I'll get back to my lecture. So if we come back to this equivalent circuit, we now realize we have now two circuits. That is, we have the stator circuit, we have the rotor circuit. Analytically, these two circuits are at 50 Hz, right? This we have achieved through this little bit of mathematical playing around. That is, we've just moved the slip term, and therefore we have made it appear like the rotor circuit is at 50 Hz. Now, what is the advantage of this? The advantage of this is that now it is possible to merge these two circuits. We can. How? Remember, the stator and the rotor now appear almost like a transformer, right? This is still an induction motor, right? It's very important to understand this is an induction motor. Physically, it is still an induction motor. This will rotate, the rotor will rotate, and because of which the induced EMF and the currents in the rotor will be at a different frequency than the stator. This does not change. Physically, nothing changes. Only analytically, it appears like as if now the induction motor is almost like a transformer. Why? Because both of them appear to be now at 50 Hz. And when we have a transformer, we've already seen in a transformer, in many transformers, we can always define a turns ratio. So let's define a turns ratio in this case. So for example, if I come here, I will say turns ratio K is equal to ES divided by ER, right? And of course we can also say NS divided by NR or whatever, right? Now it's important to know that the rotor is a squirrel cage induction motor, so therefore you don't really have the same concept of number of turns, because these are just rotor bars that are short circuited. So therefore you have to think of some kind of an equivalent circuit. But for now, don't think about all this. This is just an equivalent definition when we talk about transformers. But we can always define this turns ratio. So this turns ratio K is just like a transformer to say that ES and ER are now related by this turns ratio, right? So for example, what this means is, I could just come here, I could write that there is ER dash is equal to ES divided by K, right? This is the transformation, right? This is the transformation of my rotor equal or rotor induced EMF to the stator side, and that's just following this particular definition. Now it's important to understand that this turns ratio is just a definition. We can reverse it. We can say K is equal to ER divided by ES. That's also perfectly okay, right? And in that case, all you have to do is just reverse this. In that case, ER dash will be equal to K into ES. So now the question is, what do? We have now this definition of ES divided by ER, which means we can now transfer all our terms in the rotor side to the stator side, just like we did for a transformer. In a transformer, you can refer all the parameters on the secondary to the primary using your turns ratio, right? And we can do exactly the same thing here as well. So what does that imply? What this implies is that if there was a rotor current, right? Because if this is how we've defined K, and therefore this is how we define the rotor current. So which means that this rotor current is equal to, or rather rotor induced EMF is equal to an induced EMF ES divided by K. Alright. So essentially what this means again is that, or rather, let me remove this for now. What this means is, if I were to refer my ER, this induced EMF, if I want to take it to the stator side, I can do it by this computation. And the reverse is, or we can also do the same for current. But for current, we are going to reverse this turns ratio. So it becomes K into IS. Now, with all this, what am I trying to do? What I'm trying to say is, we now have an induction motor behaving very similar to a transformer, where we can refer any one side to the other. So we can now merge these two circuits, take all these parameters on the rotor, move it to the stator, and therefore bridge these two circuits together. Right? So we've already said that we can refer these two. So let's get rid of this. And let's just merge it. Because we've defined it. We've defined this particular induced EMF, and therefore we say that whatever is the induced EMF here will also be the induced EMF of the rotor, and therefore we are referring all the parameters. So we need to define new parameters, because these parameters are no longer in the rotor, they have now been transferred to the stator. So I'm going to say here LR dash and RR dash. So how do I arrive at these? Again, this is been discussed before. I'm kind of running out of space. Okay, let me talk about it here. So again, if we use these equations, right, we say that ES is equal to K into ER. What this means is that any voltage on the stator is going to be K times the voltage on the rotor. Right? So if there is a voltage on the rotor, such as the induced EMF, this induced EMF, and if I wanted to transfer it to the stator, I would have to multiply it by a factor K, right? Because that is how we are defining the turns ratio. Similarly, if there is a current in the rotor and we want to transfer this current to the stator, then I would do exactly the opposite. I would divide the rotor current by K, right? This is just transferring. Now, when you transfer anything from the rotor to the stator, you do not replace the subscript by S. What we do is we just define it as ER dash. Similarly, we would define this as IR dash. Oh my God, just a minute. IR dash. So what we have done is, if there is an induced EMF or there is a current, these induced EMF or current in the rotor side can be transferred to the stator by just multiplying and dividing by the turns ratio, right? So now the question arises, what do we do about the impedance? Because remember, we have this inductance and resistance that we need to deal with, right? So quite obviously, ER dash divided by IR dash is equal to, all we have to do is check out this, is equal to KER divided by IR divided by K. And this is merely is equal to K raised to 2 ER divided by IR, right? Because this K in the denominator goes to the numerator. So what this means is, if I want to refer any impedance, this could be a resistance or it could be a reactance, all I have to do is multiply it by the square of the turns ratio, right? I have to multiply it by the turns ratio, and this is how we've simply arrived at with using these equations. And these equations again are dependent on this definition of turns ratio, which is the induced EMF in the stator divided by the induced EMF of the rotor, or the turns ratio, right? Whichever it is. So now what this means is this LR dash is equal to K raised to 2 into LR, and RR dash is equal to K raised to 2, or rather K raised to 2, K square, RR dash. So we have now, using these equations, referred all the parameters in the rotor to the stator, right? And because of this definition of induced EMF, that is with respect to turns ratio, we can just get rid of these induced EMF which we had defined here. So with this, we now have one single circuit that represents the induction motor, right? The entire circuit can be used to analyze as well as simulate induction motors, as will be seen very soon, right? Now, all of these parameters are referred to the stator and they are at 50 Hertz. The only frequency dependent term that we have brought in, or rather the speed dependent term that we have brought in, is this speed S, right? This is the only indication that this entire circuit is a rotational machine and not a transformer. If I were to get rid of this S term, this would be just a transformer, a two-winding transformer. That's it. What differentiates this equivalent circuit and makes it an induction motor with respect to rather than a transformer is this slip term, right? Because as the rotor speeds up, this slip will keep on decreasing. This term, that is this equivalent resistance, will keep on increasing, right? In a transformer, that does not happen. There is no rotation, right? Only if the load changes will the final rotor, or rather the secondary resistance, change. But here, the secondary resistance, or rather the rotor resistance, equivalent rotor resistance, will change as the rotor speeds up, right? So with this, I'm going to end this lecture. The main objective behind this lecture was to be able to arrive at a single phase equivalent circuit for the single phase induction motor, just like we did for a transformer. This is something that we can use for analysis as well as simulation. So we are now one step closer towards building our simulation model. The next step is we now have to arrive at values for all these parameters. That is all these resistances, inductances, and everything else. And that's what we'll discuss in the next lecture. This has to be done before we arrive at the simulation model, right? So if you have any doubts, please do post either in the comments or send an email or message me on social media, whichever is your preference. Otherwise, I will see you next week where we will continue with this equivalent circuit and we will start estimating the parameters of all these resistances and inductances. Thank you so much for watching and see you soon. Goodbye for now.